Hello everyone, in this video we're going to be doing a continuation of the Lewis structure video. At the end of the Lewis structure video I got to sulfate and I was like, wait, this doesn't seem right and I don't remember how to do this, so I did a little bit of research and I figured it out. And it was like one of those moments where you're like, oh duh. And the reason why I was like, oh duh, is because I've learned this before. So so I'll be going over exactly why this would not be the right answer. It's very close to the right answer, it really is. There's just one extra rule in there. There's a lot of rules with chemistry, where you basically just want to get like the most stable atom possible, most stable molecule, most stable atom. Everything wants stability, right? Everything wants to be stable. That's why they want 8 valence electrons. You know, if sodium's floating around with a positive charge, it's like, I don't like that. I'm going to attach to a chlorate. Or I'm going to attach to an hydroxide in order to gain an electron. So that's why that this is an exception, kind of, in a way. Alright, so when you're stuck in a situation where you think you have the right answer because your octets are good, it's always a good idea to check the formal charges, right? So let's do that. Let's check the formal charges of each. So the formal charge for sulfur is going to be equal to the valence electrons, so 6 minus half of the bonding, so we have 4, plus the non-bonding, we have 0. So the formal charge for sulfur is going to be, oh, sorry, it's not 4 non-bonding, it's going to be 8. 8 non-bonding, so we're going to get 6 minus 4, which is plus 2. So this formal charge in here is going to be plus 2. Oops. Okay, my computer's glitching there for some reason. What's going on? Oh, okay. Computer just completely glitched out. Alright, apologies for that. Alright, so now let's do the formal charge for oxygen. So for each of these oxygens, they're going to be the same because they both have the exact same bonding, the exact same everything. So they have 6, and they have half of the bonding, which is 2 for each of them, and then plus the non-bonding, which is 1, 2, 3, 4, 5, 6. So it's going to be formal charge of oxygen is 6 minus 1 plus 6, which is 7, which means the formal charge of oxygen is going to be minus 1. So each of these oxygens is going to have a formal charge of minus 1. So you might be looking at this and you're like, Grace, why is this an exception? Because if you add up all those charges, the formal charge of this is going to be minus 2, which matches what we were told to draw. But there is something that we can do in order to make this even more stable. So this is an answer that, you know, you might get half credit on, I would say. Like if this was an open-ended test, you would probably get half credit. But there is a way to make this better, and the way we can do that is by using resonance. So what we want to do by doing resonance is that we want to deduce the amount of formal charges throughout this molecule, right? So you can see that every single atom on this molecule has a formal charge. You can think of it as something that's like stressful, right? So a formal charge is kind of stressful to an atom. It doesn't want to have any charges at all. It wants to be stable. So when it has, every single atom has a formal charge, that like stresses out the molecule, and it's not stable. It doesn't want to be like that. So in order to make it more stable, we're going to try to mitigate, I think is the word, lessen the amount of formal charges on it by doing resonance, right? So after we do resonance, we're going to be left with a molecule that looks like this. 2 oxygens on the double bonded and 6 oxygens on the single bonded oxygens. And now let's redo those formal charges, right? So let's do the new formal charge of the sulfur. We have 6 minus the bonding, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 plus there's no non-bonding. So the formal charge of sulfur is going to 6 minus 6, which is going to be 0. So that would be our answer there. So it doesn't have a formal charge. Awesome. That's already great. We already got rid of one of the formal charges. Now let's check and make sure we did the rest of them right. So we know from the last problem that the formal charge of an oxygen that has a single bond and 6 valence electrons is going to be -1. So we can write these ones as -1. So let's check the formal charge of the other ones to make sure we did this right. Formal charge of the oxygen that's double bonded. I'm just going to put like a double bond there so that I know what I'm talking about. So we have 6 minus half of the bonding. Half of the bonding here is going to be 4 plus the non-bonding, which is 1, 2, 3, 4 plus 4. So this is going to be 6 minus 6, which is also equal to 0. So that's great. So we got rid of 3 of the formal charges, which is awesome. So this would be our most correct answer, just due to that stability fact in there. But yeah, so this one is a bit of a tough one. You know, there's a lot of things going on in it. You have a formal charge you have to account for. You have multiple formal charges that you have to remember that you have to mitigate those formal charges in order to make the atom even more stable, or the molecule even more stable. And then you have to remember how to do that. So this is a very, very tough question. So if you are able to do a question like this, I think that you're all set with your Lewis structures. Again, there's a lot of exceptions that you have to remember from the previous video, but if you understand this, then I think you are all set. And it's definitely a great idea to practice Lewis structures, because there's always going to be little exceptions that are hard to remember, so it's great to get some practice in with that. So I appreciate you watching these videos, and thank you all for watching, as always. And if you guys have any questions, please let me know. Thank you.